sense of kind of the geometry here. So, okay, what does this thing look like? So first off, it's roughly speaking a kind of cylinder, a little bit like this. It's probably about this size. It has a small opening at the front end, and the front end is going to be directed into the fluid as you're moving forward in the fluid. So there's a small aperture here. That aperture is connected to an internal tube. So now we're looking inside this thing. And then the tube itself kind of undergoes a U-turn and actually goes around a kind of U-shaped, up here maybe. And what else do I want to draw on this? I want to draw on this that it's kind of connected to this. So it's connected to the interior of this. That is the back end. And then the last thing I'm going to draw on this is there are usually a series of openings in this outer kind of sort of somewhat conical section cylinder. All right, so let me try and describe this one more time now that I've drawn it, and see if I can get across exactly what this is. So this whole thing is going to be geometry like this, okay? So it's somewhat conical at the front. There's an opening here. It's connected to a tube which is solid, but runs through the center of this thing, then drops out here. There's a kind of U-bend down here. This thing comes back up, and it's connected to the larger volume of what is inside this cylinder. And then the last thing I want to draw on here is there's some fluid, some real liquid in here that is sitting in the bottom of this U-tube. All right, so let me draw a few things on here to get some color. This thing is moving forward into a fluid, usually air. So there's air coming towards this. And as the air comes towards it, it's kind of deviated for the most part so that it's flowing around the sides. So I've got something that looks like that. All right. So I'm going to compare 2 points of this sort of fluid setup. I'm going to compare this point. I'm going to compare a point that is, let's say, close to one of these openings in the cylinder sort of casing, if you will. We'll call this point A, and let me call this point B. All right. So, let's say that locally here the air is flowing around this object and it's moving locally with a speed that we're going to call v. If you think about it, that's the speed of the air relative to this object. So if you're putting this on an airplane, it's the speed of the air relative to the body of the airplane. That's the thing we're after. We're interested in finding out what this is. At this point, something interesting is going on. So remember, this is a kind of cylinder in here, which is closed. So there's air inside of here. And imagine what's happening to this flow line that just kind of comes and hits this thing centrally. And think about the point that's kind of exactly at the opening of this aperture. What would you predict is the local flow velocity kind of right at the opening there? And remember, it's kind of pushing against a stream of air that's already inside this tube. There's some liquid down here. So you can expect, if you think about it, that the air inside this enclosed cylinder inside this tube is stationary. What do you think is the flow velocity just at the point of the opening there? So the flow velocity in this green flow line. What do you think is the flow velocity? Just an approximation. So it's kind of like, let's give an example. Let me think of an example, but just imagine blowing an air stream from your mouth, but you're closing it onto the opening of something like a bottle maybe, or a soda can that's filled with air, and you're kind of blowing onto it just through the aperture. What can you sort of imagine is the flow velocity right at the point where it kind of meets that static volume of air that's inside the soda can?
It's very low.
It's very low.
It's like
right?
gliding all the air that's there.
It is. So in fact, the velocity here at this point is approximately equal to 0. So you can see there are a bunch of approximations going into these things, but it turns out this works surprisingly well. All right, so I've got a flow velocity of point A, which is close to 0. I've got a flow velocity of point B, which is whatever the airspeed is relative to this thing stuck on the outside of the airplane. So in fact, this is the speed that the airplane is flying relative to the air. This is a small gadget overall. I showed you it's kind of like A big. And in fact, it's small enough that the sort of vertical extent of this can be ignored, which is to say that the Y value here and the Y value of this kind of volume inside here is about the same. So I'm going to apply Bernoulli to this and see what it tells us. So we're going to write it here. I guess I've got enough space. So I'm going to write this PA plus 1/2 rho VA squared. I'm going to keep that for just a moment. Equals PB plus 1/2 rho VB squared. So again, I'm claiming that this is all at approximately the same height, so I'm dropping out my general y-dependent or height-dependent term. Then we just claimed that this thing is close to 0. So in fact, I'm going to drop this thing out and say it's approximately equal to 0. All right, so what have we learned about this? We've learned that we can relate the local pressure here, PA, to the local pressure in this region, PB, by this expression. So it's PB plus 1/2 rho VB squared. So that's the first thing. What does that suggest is actually going to happen to this volume of fluid that's down here? So I've drawn this in an equilibrium situation. So it's kind of at the same height on both sides. But given that we expect this to hold now, what do you think is actually the case in terms of what this volume of liquid down here looks like? Yeah.
The left side is going to go down so it's going to get a little bit up. And we can determine, we use that to say something about the pressure really. That was the amount like that.
Okay. So right, so there's going to be a imbalance here because of the different pressures in this region and in this region. So let's say that now this looks something like this. So it's become asymmetrical. We've got a fluid, the liquid moving around like this. All right, so yeah, sure, there's going to be an asymmetry here. There's going to be a difference in height of the liquid column on this side and the liquid column on this side. Now, this is supposed to be in static equilibrium. Be careful about this. So there's obviously air flowing around the outside, but when I look in this region, I've got essentially no air flowing in here. In this volume, I've got essentially no air flowing in here. So I should imagine that this thing is static. And so what I'm going to do is look now at this and ask the question, what can I say about the pressure here versus the pressure here in terms of the height of that fluid column, okay? So let me write this as a height h. And just now focus on this liquid part and tell me what I can say about the pressure here versus the pressure here. And how can I relate it to h? So remember, this is just a static volume of liquid. So we're going back to our hydrostatics, if you like. Presumably what I can say is that the pressure on one side is the pressure on the other side plus rho g h. I guess it's something like that. So this is now just looking at the sort of pressure, if you like, associated with this column of height h. Is the density of the fluid, and I have to be careful now to distinguish fluid density from the air density. So there are now two fluids in here that I need to worry about. Okay? So problems like this, we've kind of done all the hard work now. What we can basically do is relate these two things together, because the pressures A and B are presumably, this pressure A here is the same as the pressure here, this pressure B here is the same as the pressure here. These are indeed the same pressures, and I can relate these two things together. So how does this pitot tube work at the end of the day? What it does is take a liquid of known density in that U-tube. Depending on how fast the airplane is flying, you're going to get an increasing differential in height between one side of the liquid and the other. So if your pitot tube can measure the height of that column difference, h, and if you calibrated this thing correctly, and assuming you know, and this is always a little bit tricky in airplanes, because of course this is strongly altitude dependent, you know how the air density changes with altitude, you can plug that in here, and simply by measuring the height of that liquid column, you can figure out how fast your airplane is flying with respect to the local air. Yeah?
Can you take into account that velocity? I'm assuming like at higher velocities that probably has a substantial impact. The small V.
Yeah.
Yeah.
So the claim is always that you're going to find a point somewhere here, and it kind of, think of this as all being the same pressure. You're kind of compressing perhaps a static air column here, but the claim is that along here it's always static, so there's no flow here. Everything inside here is in steady state. So you can claim that this is no flow velocity, so you somewhere in here, and it's probably pretty close to the opening, you can certainly say through approximation there's no flow speed.
Really? Why is that? I mean, I
Well, think about it. It's like blowing again. Think of having a container. I kind of think of a sort of soda bottle here. It's got air inside of it. It's closed. So it's closed. And this is closed in a sense because it's got a seal here in the form of a liquid. So however hard I blow into the opening on that soda bottle, I can expect that inside the bottle itself, and certainly as I get close to the opening, the air there is not moving. And what's happening is, of course, it's getting deflected off to the side. But right at the opening there, it's usually a pretty good approximation that it's got zero velocity. Yeah?
Can I ask a question about the first example?
Sure.
So, like, why are we looking at the pressure right outside instead of right inside where the...
Okay. That's the thing that I wanted to talk about. Thank you. All right, so what's actually happening here? And again, there's a lot of approximations going on. Once it's outside, we do expect that it's back at atmospheric pressure. It's back in equilibrium with the atmosphere out here. So what's happening in practice? Well, if I was way over here, where there's really no flow velocity, what I actually expect over here is that there's an increase in pressure that I would simply calculate from assuming it's at rest. So it's the hydrostatic increase of pressure with depth. So what must be happening in practice is as you get close to this opening, the pressure, there must be an internal pressure gradient here. So it's going from being whatever the pressure would be for a static volume of fluid to atmospheric pressure outside. So that's something that's very hard to calculate. Certainly we could model it in some way, but it's hard to calculate. So what I want you to imagine is as you get close to this aperture, there's a pressure gradient where the pressure is getting less and less and less compared to what it is just based on hydrostatics. It's getting less and less and less until it just comes out of here, and you know by the time it comes out, it's back at atmospheric pressure. So for us, what we can imagine is as the pressure is decreasing here, the flow velocity is increasing. Again, this is probably very much in line with your intuition. But what we're typically asking here is what is the flow velocity once I get outside? And for any practical device, that's the thing that typically we care about. Okay? So that was the point that I wanted to talk about, this conclusion that there must be a pressure gradient in here. And the only way to handle that cleanly turns out to be the case that we might actually be interested in is once the fluid gets outside and we're back at atmospheric pressure. Yeah?
For the pitot tube,
Yeah?
will it also work if the plane is
Upside down? Sure. Sure, why not? There's nothing here that cares about whether it's being in the normal orientation or upside down.
Shouldn't the liquid not work?
Oh, I see what you mean. In that sense, yes, you're right. Then you'd be in trouble. Good point, yeah. It's actually an interesting question because, of course, there are some airplanes, the acrobatic airplanes, that can fly upside down. Possibly they have pairs of pitot tubes that can work in possibly different orientations. I never thought about that. Yeah.
pressures are all.
Okay, so equalities and pressures, yeah, and this is always hard to kind of draw exactly what I want this to represent. But what I'm claiming is that the pressure here is also the pressure here. This is just a kind of smallish sort of cylinder filled with air. So there's no reason really, once this thing has reached equilibrium, why you would expect any pressure gradient here. So I'm expecting this is a constant pressure volume inside the tube. And then here, this one's the one where I've drawn this is maybe a little bit harder to get. This is connecting to that larger internal cylinder. It's got some holes in it. So whatever the pressure is here is simply the pressure everywhere inside this cylinder, which is again, presumably the pressure just at the point where it's able to the airflow outside. So I'm assuming constant pressure everywhere inside that hatched area, plus constant pressure everywhere inside that alternately hatched area there. Okay, so I'm going to pause here and just say a couple of concluding comments about fluid flow. I realize I kind of took way longer on this than I expected, so I'm not sure if we're going to work through that problem. Maybe we will. Just take a look in my notes at a couple of other fun examples of how Bernoulli can be used in practical settings to do surprising things in some cases. And then for those of you that are interested, just following on the introductory comments I made, there's a couple of pages in my notes about some more realistic aspects of fluids, which is optional. So if you want to take a look at it, that's great. But it's also fine if you do not want to do that. All right. Yeah.
So how would you measure the vertical velocity?
So how is this done in practice? As far as I know, slightly embarrassing. I should know this. About 5 years ago, I learned how to fly airplanes, and I should know the answer. I think the vertical velocity is simply calibrated by a measure of the ambient air pressure. It's actually done as simply as that, at least in sort of traditional airplanes. These days, of course, many airplanes use GPS, and that's obviously an easy way to find out speeds in any direction you want. But in the old days, it used to actually be simply based on the change of ambient pressure, calibrated in some way. In fact, that's an interesting point. If you're flying airplanes using that, you have to always make corrections depending on things like, obviously, the local atmospheric pressure. Of course, that varies. But that is how it's done traditionally with a vertical speed. All right. So lots of fun stuff here with fluids, but at this point I think I'm going to move on. So there are two problems in my notes here. Work problems using Bernoulli. The one I was going to do in class kind of coupled this sort of problem with the continuity equation. It's kind of a nice problem, so please take a look at that, work through it if you can. And there's a second work problem in my notes, maybe not quite as interesting, but at least take a look at the one that is the first work problem in my notes. All right. So, concluding questions on anything to do with fluids. Okay, let's turn our attention to gravitation. So we're going to be spending a lot of time this morning talking about Newtonian gravitation. And then on Thursday we'll talk about some more recent descriptions of gravity and some surprises about gravity. It turns out it's something that we understand much less than we might have thought. Okay, so where have we come across gravity so far? Really in the near Earth approximation. And by this I mean near Earth's surface. And all we've done is basically think about gravity in the context of the local acceleration that gravity provides to any object near the Earth's surface. So let me say that phrase again. We talked about gravity so far in terms of the local acceleration due to gravity near the Earth's surface. That's what G is. So this is the local acceleration. Due to gravity. So what is this? It's talking about a force between some object of mass m, and we're putting it near the Earth's surface. And as we know, we're always saying that this gravitational force is kind of pointed vertically downwards. And if you think about it, what that's actually saying is it's pointing towards the, let's say, the geometrical center of the Earth. Okay? So it's directed towards the center of the Earth. That turns out to be correct, simply because to fairly good approximation, the Earth is a spherically symmetrical object. Okay, so this is what we know so far, but it turns out there's a much more general statement of Newtonian gravitation, and I'm just going to introduce it in the following way. Okay, it's not a smart place to write it, but let's do this. Okay, so a more general expression now for gravitational force. So let's explore this briefly. I imagine many of you have seen this before. So it's talking about the gravitational force between two masses, m1 and m2, and they are, at the moment, going to be considered point-like masses. They are separated by a distance r. Okay. Now, gravitation has kind of interesting feature. It turns out that gravitational force is always attractive between massive objects. So in that sense, I can represent this force by these red arrows. And what you see is this is a kind of reciprocal or mutual force, right? So object M1 in some sense is attracting object M2, or vice versa, object M2 is attracting object M1. So this force is equal and opposite, and it's acting obviously on these two masses. Okay, so fairly straightforward. It tells us about the magnitude of these things. It tells us about the dependence on the spatial separation of these two objects. We've got a constant of proportionality here. This is the Newtonian gravitational constant. Let me just check my notes here to make sure I get the numerical value correct. It's okay, all in SI units. So, what's the takeaway from this first off? So the magnitude is in some sense kind of driven by this constant. Just take a look in SI units. What is the exponent here? 10 to the minus 11. Okay? So if you're thinking in SI units where we may be measuring masses in terms of kilograms as our kind of base unit of mass in the SI system, and we're talking about separations of the orders of meters, again our base unit in the SI system, what we're seeing is that the force between kilogram scale objects separated by meter scale distances is pretty tiny. It's of the order of like 10 to the minus 11 newtons or something like this. So this is kind of a key observation. At least in this measurement system, this is kind of a weak force simply because of this gravitational constant. All right, so what have we learned? Mutually attractive force, proportional to the masses of the objects, inversely proportional to the distance, goes as the square of the separation, and that the force intrinsically is pretty weak. So this is Newton's more general gravitational expression, and this is going to allow us to extend our sort of study of gravitational systems, not just from objects near the Earth, but to objects on all scales. And so, to as far as we know, this is operating pretty much on all scales. I'll talk more about this on Thursday. There are some interesting ideas around these days that maybe say that this Newtonian gravitational behavior doesn't actually work on very large scales, but it's probably not true. So it's going to hold over all scales of objects. So this becomes important when we're dealing with gravity beyond just near-Earth systems. So when we're talking about systems of planets, solar systems, when we're talking about gravitationally bound clusters of stars and things like galaxies, when we're talking about gravitationally bound sort of clusters of galaxies, we probably know that such things exist, and in fact in the universe as a whole. So this idea is that this general form of gravitation holds over all scales in nature. So this now is not a special case. This is supposed to be valid over all scales. Okay? All right. So let's assume that's the case. Again, I'll talk about maybe some ideas that it isn't on Thursday. One addition that I want to say about this, and we'll talk a little bit about it on Thursday, but not too much, is that this also holds for objects that are not point-like masses. But anything that is a spherically symmetrical mass distribution. Okay, so we're not just confining ourselves that we can treat as point-like objects, but we're going to look at things that maybe have substantial radii themselves. You can start to imagine something that looks like this. This might be, for example, an Earth and a Moon, M1, M2. One thing I want to draw your attention here that is going to be important. If we've got spherically symmetrical objects like this, the R value that is going to hold is still about the distance between the centers of the objects. And that's important, okay? So I need to put in R as being the distance between the center of this object and the center of this object. Keep in mind that that is not, of course, in general, the distance between the surface of this object and the surface of this object, okay? So just keep in mind that that's important when we're applying this more general gravitational expression for things that have real size, real radius. Okay, so, one thing I'll mention, just as an FYI, I think, here's an example of a force that is, as we saw with near-Earth gravity, it's kind of acting without any obvious point of contact between the objects. So it's an example of this action at a distance type force. We talked a little bit earlier in the semester about whether or not you might be uncomfortable about that. But it is kind of strange, right? So imagine here we are on the Earth, we look up at the Moon every time the Moon rises. We know that the Moon is gravitationally bound to the Earth. And of course they're 250,000 miles apart. What is it that allows that force to be exerted? So we'll talk a little bit maybe about the idea of the gravitational field. But I just want to give you an FYI about other ways of thinking about this, and we'll talk about one of them on Thursday. Does anyone have any thoughts, maybe based on things you've read or heard, about ideas about how gravity might be kind of transmitted between objects? How is it that the Moon knows that we're here, for example? Yeah?
Graviton?
Graviton, it's interesting. What's a graviton?
Like a particle that just comes down.
Like a particle that does gravity stuff. Okay. Not a bad definition. Okay, yep. Could be so, yep. Gravitational waves. Interesting. We'll talk about that for sure on Thursday. Other things.
Isn't it like massive objects or the space around it, and so that's how objects at distances?
Okay. So massive objects walk the space around them. And so somehow that's how gravity is felt. Yeah, that's true. Any other inputs there? I saw a cluster of hands up there. Go ahead.
Something about warping space-time.
Okay, same idea. Somehow that we're warping space-time. Yeah, so in fact, pretty much everything you said is a plausible way of thinking about gravitation. So it's one of these action at distance forces. Strange. How is it mediated? Yes, it's possible, perhaps, and people have tried to develop this idea that it's mediated by the exchange of particles between the masses, and that become known as gravitons. Not